Today I will present SCORE, Soccer Curriculum for Ordinary Affect Recognition with Evidence. The key message is that soccer affect recognition should learn from verified visual evidence and stay conservative when the evidence is ambiguous. In broadcast soccer, a model can sound fluent when the clip itself is weak, distant, or occluded. SCORE turns this rehabilitated corner into three-stage curriculum. The first problem is that fluent does not mean grounded. Video language models often produce plausible answers even when the visual evidence is incomplete. Soccer broadcasts make this worse. Wild shorthand facial cues, occlusion interrupts the player, and fast edits remove context. The model may rely on priors about common match narratives. So the question is not only what emotion is predicted, but whether the prediction is visually justified. The task uses short soccer broadcast clips. Each sample is 2 seconds around a key event, represented by 8 fixed frames. The labels include 4 emotions: joy, claim, sadness, and angry, plus a 3-level ordinary intensity. Table 1 also shows evidence metadata such as shot scale, occlusion, and home or away role. This lets evaluation separate easy clips from ambitious ones. Figure 1 gives the full soccer framework. The preparation pose provides sports video frames and verified supervision. Stage 1 learns grounded behavior through the Visual Evidence Concentrator, or VEC. Stage 2 uses ECPO, where preference updates are controlled by collaborated evidence. Stage 3 predicts effects and reports uncertainty. The shared principle is simple: update when the evidence is verified, and avoid risky updates when the evidence is weak. Stage 1 focuses on visual evidence compression. Most visual tokens in soccer broadcasts describe background elements such as grass, cloud, and advertising boards. Equation 1 defines the frozen visual features and projected tokens. Equation 2 defines the VEC, which uses learnable queries and attention to extract compact evidence tokens Z. These tokens become the visual context for the language model, making the adaptation lighter and more player relevant. Stage 2 is evidence collaborated preference optimization. Algorithm 1 first extracts frozen evidence tokens, then proposes and verifies a grounded package. A counterfactual negative response is created through a minimal factor edit. The model then computes evidence spots for both response. The important step is the gate. The preference update is applied only when the positive response is clearly better spotted and ambiguity is low. The ECPO formulas explain the conservative update. Equation 10 defines a gate based on evidence advantage and ambiguity. If the advantage is too small or uncertainty is too high, the gate becomes 0. Equation 11 then multiplies the preference loss by this gate. As a result, ECPO does not learn from ambiguous preference pairs, which reduces the risk of amplifying hallucination descriptions. The qualitative example shows why this matters. In the ambiguous clip, baseline models add plausible but unsupported events, such as crowd reaction or an inevitable turnover. These statements sound natural, but they are not clearly visible. SCORE gives a more restrained answer that stays closer to the evidence. For sports analytics, this kind of grounded modesty is valuable. Stage 3 turns grounded representations into effect predictions. The model predicts both the emotion class and the ordinary intensity. The ordinary objective is important because dismaking low frustration for high frustration should be penalized more than a small intensity error. The WOER head also uses evidential regularization, so the model is discouraged from being overconfident when the clip is visually ambiguous. Figure 4 shows the reliability trade-off. The target coverage is 90%, meaning the prediction interval should contain the tree intensity about 90% of the time. A trivial solution would be to output very wide intervals, but that is not useful. SCORE aims for reliable coverage with narrower intervals. Around the target coverage, the curve shows a meaningful wide reduction compared with the baseline. Conformal formulas explain how uncertainty is calibrated. A separate calibration split. The model computes non-conformity scores for the distance between predicted and true intensity. One tail of these scores becomes the threshold for test time intervals. The final interval is clipped to the 1 to 3 intensity scale. This gives a distribution-free reliability line, reported with coverage, interval weights, and ECE. The main experiment table evaluates both general capability and Soccer-specified reasoning. Bench Mini and Video MME check whether adaptation causes catastrophic forgetting. Table 4 reports Soccer VQA results, where eCPO reaches relative score of 71.3. This improves over data-only SFT, DPO, and eDPO, suggesting that evidence-gated performance learning adds value beyond the simple supervised tuning. Table 5 focuses on effect recognition. The top part lists standard video baseline treated on the effect labels, while the lower part shows score stage-wise upgrades. Stage 3 with WOER reaches the strongest row effect metrics, include macro F1 of 61.3 and MAE with 0.47. The conformal variant selected trace point accuracy for collaborative reliability, which matches the reliability first motivation. Table 6 addresses teacher dependence. The proposal source is varied across proprietary teacher, open teacher, and minimal human settings. In each case, score improved over the matched naive SFT baseline. Coverage also reaches the target 0.90. This supports the claim that the curriculum and evidence control are not merely distillation from a strong closed source model. Table 7 explains why each component is needed. Without VEC, VQA drops and hallucination rises. Without evidence collaboration or the risk gate, reliability degrades because ambiguous updates can affect the policy. Without conformal collaboration, the model loses the coverage guarantee. The emulation therefore supports the full design, better evidence tokens, safer updates, and measurable uncertainty. The takeaways are threefold. First, VEC compresses noisy broadcast tokens into compact evidence tokens. Second, eCPO updates the model only when the evidence advantage is clear. Second, eCPO updates the model only when the evidence advantage is clear. Third, WOER plus conformal collaboration makes uncertainty usable. The final message is that reliable soccer effect recognition needs evidence control. Bigger models alone are not enough if they cannot distinguish visual evidence from plausible narrative pairing. Thank you for listening. Questions are welcome.